Anyone have any questions from anything we covered yesterday before we dive back into reinforcement learning? As for the state of the class, I think everyone should now have a group. We found our two missing people from the first day, and they're, I think, now fully integrated. So everyone should have at least a 3-person group. Any questions or concerns? Still the first week, nothing hugely in sight at the moment. So yeah, no class tomorrow. We will be meeting on Friday to talk about your game ideas. So prepare for Friday, just have a scoped idea of what your project is going to look like. Have an idea of what you'd like to have accomplished within the next week, and have an idea of who's doing what, who's responsible for what aspects, just to be able to have that level of organization. And I'll meet with each of you and try to determine either poke holes or come up with some extra brainstorming ideas of what I think would be cool, or a way to tie this all together in a way that either makes it more feasible or more fun. So I really do look forward to seeing and hearing your ideas. And if there's anything to demonstrate at that point to show off, I'd love to see it. So that's the plan for Friday. I think anyone who can be here should be here for that, just because when you're here, you take that in rather than hearing it from someone else. All right, diving back into reinforcement learning. Last we were talking about value functions for tic-tac-toe. We had an idea here that we're going to relate a probability of winning to each state that we could be in. And once the game is over, we know the probability of winning. If you have won, the probability of winning is 1. If you have lost, the probability of winning is 0. Every other value we're going to initialize to 0.5, and we're going to then let our experience tell us what the actual probability of winning is based on a history of being in that state and choosing whatever actions that we take. So we had a value function. This was the update function to the value function. We looked at extreme values of the learning rate. If the learning rate was 0, no new information caused us to change our mind at all about anything. If the learning rate is 1, then we're very much overreacting to the last data point that we got. And we're just replacing the old value with the new value. And that's not good either. So we wanted something in between. We found a big flaw in this plan in that we may not explore all of the optimal actions. It could be that our experience has led us to randomly pick ways to lose the game when there is a way to win the game from that state. And if we play in such a way that we lose from there, that is what we are changing with regards to the value of the state. We're using the experience of what happened, not what could happen or what would happen. So we're going to start today with a fun exercise. We're going to go gambling. Always a fun time. It's even more fun because these slot machines are on free play. There is no real gambling. You can imagine that I give you this gift. You've won this gift from the casino that says you may play a slot machine 2,000 times. But there are 5 different slot machines, and you have 2,000 total plays. What you know about these slot machines is that they may have different reward distributions. So a mean payout, a standard deviation payout, if they're not normally distributed, then we could apply the central limit theorem and map them onto a normal distribution and map them back. But they have some distribution of payouts. We don't know what they are. We have to learn them from practice. So the task that I will set to you is, what algorithm would you use to maximize the amount of money that you walk away with? It's on free play, so there's no cost to playing. It's just a matter of, can you identify which machine gives the most money on average and play that for your remaining time? If so, how do you figure that out? How do you know that how you're figuring it out is optimal and is better than someone else's strategy. So take some time to think about this and talk amongst yourselves. See if you can determine or find a strategy that you think is very good or maybe even optimal.
When you say mean payout, are you talking about it like if I played it 2,000 times, that's the mean of like the total amount of times with the individual machine? Or
Yeah, maybe theoretically, if you could visualize the distribution, what would the expected value of that distribution be? But we don't know that it's normally distributed. We don't know. So for instance, one of these machines, let's call it machine number 4, might be a lottery simulator where it gives you nothing. 4,999,999 times out of 5 million. And one time out of 5 million, it gives you a massive jackpot. Another one might be completely normally distributed. Another one might give you 5 cents every single time you play consistently. No deviation whatsoever. You don't know the distribution, you have to determine it from experience. Or guess it from experience. As you're getting that experience, you want to be changing which machine you're playing to try to maximize the money that you walk away with, given that you only have 2,000 tries before you're kicked out with the money that you earned. Yeah, talk amongst yourselves. This is way too quiet.
Yeah, it should. That's what I was right.
That limiting space on potentially students. Use of how we start to see my impact desires. Right, because there's actually the people for it, because you saw that money, yeah, you can buy that by and that's how we see us in the trials. Like it takes $1 that's the environment, so you play certain schemes, you provide them ability to provide camps, yeah, but it took some nobody even bad attempts, like it's a lot of attempts, but these lives, so specifically, the person is going to give a chance. That's a good piece of it. You just their salaries still nice.
How would you know if you played it 20 times, 30 times, 1,000 times and never gotten a reward from it? How would it differentiate from this machine that has a massive payout or a machine that just eats your money?
Yeah, I was just trying to keep that for.
Yeah, that's good.
Right. I mean, but if you want to go play, you get at least the part 2,000 out and get one year. Questions well, so one thing is as a vision that let this amount of capital spending on that the maximum out this lines a little from these studies. That means you got to think about it's yeah, which should just sound good strategy or just better than it, yeah, like definitely stuff there a little bit more of 125,000 then we have a lot of the things so that is how you they're fair stop changing and to be a forward
Is there any parameter about what we can assume that the mean for tabletop?
Nope.
Not at all.
Purely our experience. We know that the return is going to be 0 or positive. It's not going to, whatever this spins, when the spin stops, is you now owe me money.
Okay. Yes.
So like, let's say it's like 10 times. And there was so many versus the application should be. You say, something else, 3 apps.
Well, what I guess I meant is that you don't have any data until gives you nothing.
So I think you're right, it's just a manual process.
And then I guess you could, but I can train it. So, okay, cool.
And then you put 2 other say one, then you can like, that's. These are.
Anyone think they have an algorithm that could beat anyone else's or everyone else's?
So. I feel like I've talked about this with you in the past, so I feel like I have a head start compared to most other people on this information.
I talked to you about exactly this.
Yeah, I'm pretty sure, because it was related to the optimization that you have in mind for like CS majors, like the perspective on life.
It is different from that.
Interesting. Okay.
There is an optimal answer to this.
What is it?
I will reveal it eventually.
I mean, what I came up with wasn't very complex, but like allocate like say 50 plays to each machine.
Okay.
From that sample size, determine like what are the chances of getting a certain payout or how much money you're making on average from those plays.
Mhm.
And then with your remaining 1750 plays, go only for the slot machine that returns the most. And then
What happens if you get unlucky from that and it dips below an average of another machine? Do you switch?
That's a good point.
What happens if you were unlucky in your first 50 and one machine that has a very high expected value, but a large distribution, you happen to get on the lower end of that average. So the average looks worse than others, but it's actually the best machine. And as an average that's different, how would you know that the sample size, like why did you choose 50? Is 50 enough for this number to stabilize? What assumptions are you making about the underlying distribution when a sample size is 50? 50 is a good enough estimate to get a real value. If it's normally distributed, 40 data points is enough to be able to estimate a mean and a standard deviation nicely. But if you're playing the lottery machine that only has a 1 in 5 million chance of winning, now you need a much larger sample size in order to be able to approximate the expected value.
I mean, since we only have X number of iterations, right, then we have a limited time scale that we have
We
to
do.
keep in mind.
We do.
So what if like a constant? To be honest, I don't know how much of this time that would be optimal to spend, but like in my mind, like I don't know, if we said 50% of the time would be spent, or I guess we start in.
See how.
Yeah, experimentation, and then 50% of the time would be like exploitation.
Yeah, so we talked about exploration and exploitation, so maybe breaking this down into an exploration phase and an exploitation phase. I like the idea. I think that would produce a good result.
That's what I would go with. If someone came up to me on the street and said you have 5 minutes.
Yeah.
But
Yeah.
obviously, build complexity.
So I'm going to present an idea, and we are going to find some weaknesses with this and an idea just to start, and then I will show how this is done in practice, what the optimal way is. It turns out that the algorithm that optimizes this, the paper that wrote that was my qualifying exam for my PhD. Random aside.
Nice, you want us to figure that out in 14 minutes?
It's reasonably intuitive, which I like. So we're going to look at an epsilon greedy approach. And epsilon greedy just says, as we do this, we're going to maintain estimates of what we're going to call action values. In tic-tac-toe, it makes much more sense to keep track of action values rather than state values. A state value is the value of being in a particular state, and that is hard to know without a policy. Because if I act randomly, the value of being in a state is different than if I act intelligently. If I'm 1 move away from winning, if I act randomly, I'm going to have a chance of winning 1 over the number of places that I could move. If I act intelligently, I now have a 100% chance of winning because I can win in 1 move. So trying to figure out the value of a state is based on this concept of, well, what is my action selection function? If instead of trying to optimize this for the values of states, if I instead look at state action pairs, when I am in this state and I make this action, How good is it? That tells us if that action leads to a victory, we're good. It doesn't matter how I selected this action. The fact that I chose this action tells me how good it is to have selected that action in this state. So we're maintaining estimates of state action pairs. We're in a state and we choose an action from that state. What is the value of that? With some probability that we're going to call epsilon, we're going to take the action that maximizes the expected reward. This is an exploitative action. So we're going to exploit. With 1 minus that probability, we're going to take a random action. We're going to explore. So epsilon, that probability we exploit, 1 minus epsilon we explore. We can ask the question maybe, why is exploration important here? Why not just exploit? Why do we need to explore in a situation where we're playing slot machines and trying to maximize the money that we have? Yeah, you start out knowing nothing at all. And even if you have a particular sample of distribution from each, how sure are we that we know what the best machine is? If you have had 100 plays on each machine, how sure are you that you know the best machine? If you've had 1,000 plays on each machine, how sure are you? Are you ever 100% sure you know what the best machine is?
I mean,
Can you ever be 100% sure?
I think so. I mean, doesn't this get into like non-determinism where it's like, well, what if the next one's the big hit? So I can never truly understand like if a slot machine's truly fully understood.
Yeah, we don't know if we've been unlucky. We don't know if there is a very unlikely outcome we have not seen. Without an infinite number of plays, we do not know the underlying distribution for sure. We might be able to come up with an approximation of that based on the information that we have from the sample that we've played, but we should never be 100% sure of the underlying distribution. So because of that, we will need to explore in order to get more sure. This gets us into a concept that we'll go into in a lot more detail when we start looking at this in mathematical detail, which is the concept of immediate rewards versus future rewards. One way I like to think about immediate rewards and future rewards, I give you two options. I can give you $5 today, or I can give you $5 in 10 years. Which one do you pick? Today? Why?
There's an immediacy, like, oh, this would help with something right away.
Yeah, you could, worst case, you can invest the $5. It would be worth more than the $5 that I would hand you in 10 years. You could look at inflation and recognize that $5 in 10 years won't be worth what $5 is worth today. You could look at, well, I might be dead in 10 years and I don't want you putting $5 on my corpse. I want the chance to spend it. We would hope that you're around in 10 years, but it's not guaranteed. So for all of those reasons, you should prefer the $5 today. But there are some times when you don't want to maximize for the immediate term. If I tell you, you give me $5 today, I give you $1,000 in 10 years. Who's willing to take that?
Take it as a now or taking as
To do this, to give me $5 today with a written legal guarantee that I will give you $1,000 in 10 years. A lot of people. Does that help you or hurt you looking at just today?
Technically, it's like, but it's $5.
Right. It's not you can start to prioritize future rewards if it offsets the chance that you won't be around, the minimal hurt that it is in the short term versus the larger benefit that it would be in the future. There exists such a way that you would want to prioritize the future at the expense of the present. Kind of like a mistake. If you make a mistake in real life, it's an exploratory action. Maybe you feel a little bit worse. It wasn't the best move that you could make, but you learn more about yourself through the failure that you experience, and you can now exploit that failure in the future, the knowledge that you gained from that failure, to do better for yourself moving forward. Societally, we focus on mistakes way too much. Mistakes should be applauded as long as it doesn't kill you. Darwin Awards should still be funny. Just like we did before, let's look at extreme values of a learning rate. What happens if epsilon is 1? In success. That means we're exploiting. We are done learning, never want to learn another thing in our life. We're going to take the experience that we have and we're going to apply that experience to every decision that we make. None of that experience is going to teach us anything. We're just always going to do the best that we possibly can with the knowledge that we have. What about an epsilon of 0? Random actions. Doesn't matter how much I already know, I'm just going to act randomly. If some of those turn out to be a mistake, I'm not going to learn from it. It's not going to change how I behave. I will continue to act randomly. So just like before, a value of epsilon between 0 and 1 is usually, you don't want to be at the extremes, but we want to be closer to one end than the other. We'll look at what that is. What's bad about epsilon greedy? There are two main things that I want to focus on that are large weaknesses with this proposed method of a way of optimizing slot machine pulls. You can imagine doing this, finding a value of epsilon that works well. We're going to pull the machine that has given us the best rewards so far with probability epsilon. With probability 1 minus epsilon, we're going to use a random number generator, pick between 1 and 5, and play that machine.
To a certain extent, like no matter what option that you choose for your greedy value of E, you're going to be biased to either successes or failures. So if you get an immediate set of successes, like you get 3 in a row, you're more likely to just stay locked into that machine, even if it's going to be bad for you detrimentally later on. And if you suffer like some unfortunate consequences early on, you're more likely to avoid that machine, even if it is the best overall. You just got unlucky.
Is that inherent in the decisions that we're making in epsilon greedy? Is there any really way around that issue? If we get unlucky, how do we know that we got unlucky? Or are not just playing a worse machine?
Yeah, more exploration, which that's fair.
If you choose the more exploration, though, are you exploring a machine that's just a worse machine, saying that I think I got unlucky with this machine and it will give me a higher payout? How will you tell the difference between those two worlds? From your shoes playing this in real time, there's no way to know. It's a great point, though. What are the flaws with this procedure? There are two large flaws that we can identify that we could reasonably easily work around.
Are you talking about the amount of exploitation or
Possibly.
limited scope?
So how much are we exploring at the beginning of this process? If we get 2,000 pulls, how frequently are we exploring a pull 50?
Pretty frequently.
1 minus epsilon? What about at pull number 1,950? Probability 1 minus epsilon when we have more information about the underlying distributions, and maybe we would be wanting to exploit more frequently. Early on, we have small samples for everything. Exploration should happen more frequently because we're not convinced of the data that we have, small sample. Later on, when it's almost time to go home, we should probably be taking advantage of the data that we've gathered throughout our time playing these slot machines and assume that we've found the best way to win. We should be exploiting more than exploring at that point because there's not enough time left for the exploration to lead to profit. Even if we could find there is a better slot machine than the one that we've been playing, the chance of that is lower than it was at the beginning, and you don't have as much time left to take advantage of the information that you've gained. So it continues exploring forever, which is a good thing by itself, but I guess the weakness is it continues exploring at the same rate forever, which is not ideal. You can use a temperature parameter for this. If you've seen that in other classes, basically it starts, it's like forging a sword. You melt the steel, shape the steel. As the steel cools, it becomes less and less flexible, less and less modifiable until it is very solid and you can't move it at all. But as that temperature cools, it goes from being very flexible and malleable to being very rigid. And this is what you want to do to your exploration rate. Early on, you want it to be very flexible, where you explore a lot. But as you get more and more information, the exploration rate cools and becomes more rigid. So that is why we call it a temperature parameter. It's kind of like heating this room up to 100 degrees and then immediately setting the temperature to 50. It's going to cool relatively quickly and then slowly approach 50 asymptotically. So it makes large scale changes early and then tapers off toward the end. The other big issue is that it treats all non-greedy actions as equivalent. Let's say if machines 2 and 3 are performing very well, 1, 4, and 5 are absolute garbage. When we explore, maybe machine 2 is outperforming machine 3 by a little bit. When we explore, we should be biasing this toward the next best machine rather than just a random machine. Maybe have a proportional chance of picking each machine based on how it has performed historically. We're more likely to pick those that have been better. When we take an exploratory action, bias it towards what's likely to change your mind about what the best slot machine is and change your mind about what an exploitative pull looks like. So epsilon greedy is a very easy implementation that works okay in practice, but it is still not optimal. The optimal algorithm is UCB. To talk about this, we'll first define the concept of regret. To be able to quantify regret, we have to know the underlying distributions. Imagine at the end of the 2,000 polls that you got, you get to see the underlying distribution. And you could see what it would have been like to play this optimally. One of the 5 machines is going to have the highest effective value. And as that has that value, that's what you should have picked all 2,000 times. How would you have known that from the beginning? You couldn't possibly. But that would have been the optimal way to play. So regret is just the difference between what you could have received on average if you had played the best that you possibly could have and what actually happened. So we should try to minimize expected cumulative regret. You're good. So what we can do here, we can take a big issue with our past and use optimistic initial action values. When we back talking about tic-tac-toe, we initialized values to 0.5. This was actually a terrible idea. Remember that this is what caused us to not be able to explore all optimal actions. The easy fix to this is to set the initial value to the optimistic value. What is the largest value that it could possibly be? In this case, this is between 0 and 1. So we should, if we initialize this at 1, what we're doing is we are slowly letting these values converge to their true values, but you're converging from the optimistic view down, rather than from the middle where some are going to be going down, some are going to be going up. If you do this, you're much less likely to have an average that goes below its expected value until later. So you can imagine something like, I don't know if I want to go there quite yet. Don't mind me. So if we use optimistic initial action values, like that initial value of 1 rather than 0.5, what we're doing is we're promoting exploration early, because the value that we start at, 1, as soon as we lose a game, we're going to want to explore every other possibility and see what we win and lose from there, trying it at least once as those start to fall down from 1. And those that have a worse response will fall further, but we're still going to get to that point. We're still converging from the top down. So what we want here, and this is actually a terrible picture, I have a better picture that I meant to put in here, is we want to look at mathematical confidence intervals around the means of each that we have picked. Why confidence intervals? What do we know about confidence intervals? What causes a confidence interval to be wide versus narrow?
It's like the difference between the pilot, the word versus the width.
Okay. Yeah,
How confident you are that a certain outcome is going to be within these two bars? Because it can be low, it can be high, but that's like the area that you're expected to see it. If it's smaller, that means you're more confident it's going to be tighter in this area.
how do you get to be more confident?
You do more testing.
Larger sample size.
Yeah.
We have machine 1 that has a very large confidence interval, and machine 2 that has a very narrow confidence interval. That means that we played machine 2 more than machine 1. Yeah,
Think of it like if we started all at the top and the first one that you played lost, you don't have the confidence that that's where it's supposed to be. Because you haven't played the other ones or you haven't had it
right.
verify that that's.
Yeah.
Okay.
And that's the reason we use the upper confidence bound here rather than the mean. We're going to choose the 95% or 99%, whatever confidence interval you're using. We're going to choose the upper bound of that rather than the mean. And that builds the sample size into the calculation. A confidence interval will be wider, the upper confidence bound will be higher if we have a smaller sample, which will promote exploration. And as we play something more, it will tighten around the actual mean. So there's actually a very clever formula that we use to calculate the bounds of this. It's not exactly a confidence interval, but it's related to it in that this numerator grows whenever we play any machine. And this denominator shrinks this value whenever we play that machine that this is focused on. So this is the value of the jth machine. This is the mean that we've seen so far at time t from that machine. This is the number of pulls of all machines, the number of pulls of the jth machine. What this means is that the number grows and the height of the upper confidence bound grows when we don't play that machine, but it grows at a proportion of logarithmically so that we don't pick it very frequently. An important aspect of this is that we do still need to explore forever. We want a theoretical algorithm that after an infinite amount of time has passed, knows what machine is best. And the only way we can be guaranteed of that is if we have an infinite sample from every machine. But we want an infinite sample from every machine that is weighted by how good the rewards are from that machine. So we don't want to just play every machine the same number of times. We want to always want to go back to each machine, but at a proportion that is based on the reward that we have received from it so far. And that will be based on that average and the number of pulls. So you can imagine this numerator, if we start at 1/1, if we increase the denominator 1/2, that shrinks the number. We increase the numerator and the denominator at the same time, it stays the same. Later on, it may go up. If you have 1/9 and you go to 2/10, that went up. So you increase the number of pulls, the number of times for this, and you find that the upper confidence slowly shrinks back up the longer time that you don't play that. But again, it's based on the mean value of what you've received so far. So when this becomes the highest upper confidence, it'll happen proportionally to how good that is. A machine that is terrible will have an upper confidence limit reach less frequently than one that has been very good. It is an incredibly good algorithm. This is the optimal way to solve this problem. Look at the upper confidence limit of each machine based on the number of times you've played it. That'll promote a ton of exploration early. The exploration will taper off as you get more information. You will bias yourself toward the machines that perform the best when you do explore. And given that you don't understand the underlying distribution, this will maximize the money you walk away from or with and minimize that regret. Any questions on that? How it works, why it works? All right, this was expanded to work with trees, and this makes much more sense when we're looking at a game with a branching factor like tic-tac-toe. So we can now construct all possible board states of tic-tac-toe as a tree. Then you can imagine that every single one of these states has a UCB problem embedded within it, where the arms, in this case, the slot machines that you could play, are the possible places that you could place an X. So this is the equivalent of pulling arm 1, pulling arm 2, pulling arm 3, pulling arm 4, etc. 9 options for it. When we get down to however O responded to our X, there are now 7 possible arms that we could pull from here. And we could treat each one of those as a sample of a distribution from which we've played this game. We now want to return to this and figure out how good is it to be in each of these states. Where should I place an X whenever it is my turn to place an X? You'll make an exploitative action based on the upper confidence limit, an exploration-based action based on an upper confidence limit. And this process will learn forever, but will also exploit as frequently as it can possibly get away with, knowing that it wants to be 100% sure eventually. Doesn't ever get there, but it will always get closer to be performing optimally. So here's kind of bring this back together into a game. If you were designing a reinforcement learning agent to play tic-tac-toe, here's one way you could set it up. You would learn through experience how good it is to be in each state, playing each action. And over time, you would get an infinite amount of experience with each possibility. You would never stop getting experience on any particular play. So you would become surer and surer over time that the algorithm that you are performing is optimal, because you'll be exploring less and less frequently. Still infinitely, but less and less frequently as it asymptotically approaches optimal play. So every node of the tree is a UCB problem. And this would eventually perfectly play tic-tac-toe. We can finally have a computer do what a chicken can do. Yeah. It just takes a lot more work than it takes for the chicken. So there are a couple of underlying problems that we can extend this with, because not all problems map directly onto this exact kind of problem. The first is that not all problems are stationary. And by stationary, I mean that the underlying distribution stays the same over time. As you continue to get experience with something, sometimes what we're looking for is a moving target. When I talked about the concepts of utility and making decisions for ourselves, we get older, we get experience, and what we want out of life changes. So if we're trying to optimize our action functions for 5-year-old selves still, I'd just be eating candy all day, every day. I wouldn't come to work. Why would I want to do that? I would just eat candy. Since I've evolved a bit from what I want and get value out of as a child, I've had to learn how that changes because I'm not 5 anymore. An example of this, going back to the slot machine example, is imagine that every time you play the slot machine, both the mean and the standard deviation, assuming they're normally distributed, take a random walk. That means that it may increase a little bit or decrease a little bit. And now the next time you play, it has a different distribution, slightly different distribution than it had the last time you played. And then you play it again, and it's a slightly different distribution than it was last time. But that's true all of the time. How would you optimize this problem? Now, what was the best slot machine when you started might not be the best slot machine now, 1,500 plays in. How would you figure that out? What could you do to this process to optimize it for the fact that things might be changing? Any ideas? Yeah,
You have to have some kind of weight, right, to have more recent experiences.
yes,
Be weighted more heavily than past experiences or experiences that are much older.
right, because you're less and less confident that the old experience is based on the same distribution. The distance away from the current distribution, from whatever that distribution happened to be, you become less and less confident over time. And so if you weight the more recent examples higher than the far in the distance examples, then your cumulative, you have to trade off the sample size of having played this a bunch of times with this data is less relevant than this data over time. So yeah, you want to weight more recent rewards more than past rewards. Exactly how you do that will be problem dependent and situation dependent, but we're going to get into things like policies and Markov decision processes. We're going to start with a more technical version of diving into exactly how to make these kinds of agents starting next week, but I'll give you a little bit of a view into the future. So we can define a policy as just how the agent decides which action to take given the states that it's in. So as you are playing tic-tac-toe, how do you figure out which square to place something in? A policy could be, given the experience, we have an approximation for how good it is to be in the following states based on these actions. I'm going to pick the action that maximizes the expected value in the next state. That is a policy. You could also, since that does not promote exploration at all, you could use something like an epsilon greedy policy approximation, where you could say, I'm going to choose the optimal action X% of the time, and I'm going to randomly explore something that seems suboptimal 1 - X% of the time. 100 - X% if we're using a percent. I like thinking about this in terms of tying everything into real life. So if we are reinforcement learning agents, how do we make decisions in ways that when the outcome is unknown, how do we take our experience and make these kinds of decisions? We have policies of how we react to the world around us. So if you want to tell your partner that you're breaking up with them, how do you approach that? There are all sorts of possible states that could arise from that. So how do you come up with an action function for how to accomplish this? We can also talk about a Markov decision process. Just has everything you see here. It has the states, actions, transitions and probabilities, expected rewards, and something we'll talk about in a bit called the discount factor. This is the extent to which we prioritize present rewards over future rewards. If your discount factor is very high, then this becomes a multiplicative decrease in the future. So let's say something like I have a discount factor of 0.99. So something that's very close to 1. This would say the reward of the value today is 1. And if this is done over a yearly basis, the value of that same reward in 1 year is 99% of what it was today. The value that would be in the next year, it just is exponential decay as we move toward eventually 0, but it tells us the rate of fall off between prioritizing the value of the reward as it exists today, the value of that same reward as it exists some number of time steps in the future. You can imagine a discount factor that is much lower than that. Instead of a discount rate of 0.99, if you have something like 0.01, you go from 1 to 0.01 to 0.01 squared to 0.01 cubed, and that falls off way faster. In a single time step, it's worth 1% of what it was today. It's worth 1% of 1% in 2 time steps, etc. So this is just a mathematical way of representing exponential decay. And oftentimes when we're looking at rewards and those rewards happening in the future, we can use a discount factor to break ties. Should I win this turn? 3 turns. If you have a discount factor applied to the value of a win, then you would prioritize winning now versus winning in the future. Even though the outcome looks the same, you won the game. This would break that tie, and the value of that win now would look higher. This is useful in games if you actually want to create a dumb AI that wants to leave space for the player to win. It can look at and even look and say, all right, I'm actually going to prioritize winning in the future rather than now. Even though I could win now, I'm going to take actions that put it off, that open up the door for a player to come in and snatch victory from the claws of defeat. That feels good from a player's perspective, and this is one way mathematically we can make that happen. All right, that's the end of this slide deck, and I probably don't want to get started on the next one. So I think we'll call it here unless anyone is horribly opposed to that. 1 minute early. And I will see you all on Friday to show me your awesome game ideas. And then Monday, we're diving into this in a bit more detail. A lot more detail. Yay.